Hi everybody, I hope everyone is doing wonderful. So today we are going to solve this question from LeetCode, which is going to be construct binary source tree from preorder traversal. Before reading all of this description, I am going to simply take this question here, which is construct binary source tree from preorder traversal, and then I will be going here. So before understanding this question deeper, you need to understand one or two things. Well, basically, the question is asking us to construct a binary source tree, which in short form is BST. And then how are we going to build that BST is going to depend on this pre-order traversal. So basically, they have given us this pre-order traversal of the binary source tree, which you can see it here. It also says that given an array of integers pre-order, which represents the pre-order traversal of binary source tree, construct the tree and return its root. So given this binary source tree's pre-order traversal, we wanna find the or build the binary source tree itself. So if you see it here, the pre-order traversal basically is so this is the binary source tree I have built manually from this pre-order array. Now if you see it here, if we do a pre-order traversal, it's gonna be basically we will print our root first. So basically we have printed this root first here, and then we will go to the root's left side and then print its value. So we printed 5 here, right? Then we will again go to the root's left value from that root and then print its left value, which is 1. Now we will try to go again, but it doesn't have any value, which is null. So we will backtrack from here and go to our parent, and then we will call our right function or the right subtree or the right node and then print its value, which is 7 here. Now it doesn't have any value on left and right side too, and then it also has already successfully calculated the left side. We will backtrack from here and then go to 8. Now 8 has already completed its whole right section, right? Sorry, left section, right? Now it's gonna go to the right section and call this value 10. Now 10 will print itself because this is pre-order traversal, so we will print our root, and then it will call its left, but it doesn't have any left value, so go backtrack, and then it also has successfully submitted its or successfully calculated its root or from left, and then it will call for the right, then it will print the 12. So that's how we do the pre-order traversal, right? But the idea here is not to do the pre-order traversal. The idea here is to take that pre-order traversal from that given binary source tree and then construct a binary source tree from that pre-order. Now, how does that binary source tree look like from this pre-order traversal? Well, we will construct a root value initially, and then we have to basically to satisfy a binary source tree, we have some conditions that must always hold, right? For a binary source tree, it also has a root, right? Its root's left value should always be less than the root itself. What I'm saying is, if we wanna put a value in the left side of a root for a binary source tree, it should always be less than this given value, which is 8, right? In other words, the left subtree of the given root should always be less in value, and then the right subtree or the right node from this given root should always be greater than the root's value. So it's gonna be here greater than root, and we can also say it here that this is root's left, and then this is root's right. So if you see it here, is 5 less than root? Yes, that's right. So if that's the case, we will put 5 here. Now since we are doing it pre-order, so since we are using this pre-order traversal, we will again try to form a left subtree with the given value, and then since we checked 8 for 5, we have to check 5 as a root for 1, and then we will say if 1 is less than 5, then that can be our subtree or left subtree, right? And if you see it here, one interesting thing, since 5 is lesser in value for 8, that is our left subtree, right? Now 1 is less for 5 and then 8 also. So what I'm trying to say is every value on its left subtree should always be less than its parent. It should not only for one parent, it should always for every parent. It should always hold true for every parent. Now we will try to again construct a left subtree from here with the 7 value, but since 1 is lesser in value than 7, we won't be able to create our left, right? Now we'll go backtrack and then go to 5, and then it will try to construct a right subtree with the 7 value. Since 7 is greater than 5, which is true in here, and then it should be lesser than 8 though, because this whole is a left subtree, right? And that's also true, and then we will insert the value 7 here. Now we don't have anything to do here. We will go out and then, or it will return null, and then go backtrack here and then again go to the root. Now we have values left 10 and 12. Since 10 is greater than 8, we will put it in the right section. We'll try to create a left subtree with 12, but it doesn't hold true. And then since it doesn't hold true, we'll try to construct a right subtree from there, which is going to be 12. So that's how we will be building our binary search tree. Now it got a bit messy, so I will simply draw the binary search tree that I just built here, which is going to be 8 and then 5, and then again on its left side 1. Now 7 is not less than 1 or neither less than 5, so we will put it in the right section, and then again for 10 we will do it in the right, and then again 12 we'll do it in the right section. So that's how we build the binary search tree. Now this idea is the whole idea that we are going to be using, but it cannot be directly solved like that. So we have to take care of one or two things. So you can simply remember one or two things. We will be solving this problem with the idea of upper bound. Don't get triggered or worried by this word upper bound, which basically we're trying to see when we build the root, we can simply build the root with whichever value we started with, right? So since let me remove this from here, and then again try to make it here 8, 5, and then that's going to be 1, 7, 10, and 12. So that's our binary source trees pre-order traversal, right? Now we will start from this root index. For a second, I'm going to remove this upper bound here, and then also remove this everything from here. So initially we will start from our given arrays is starting index, which is going to be 0, right? And then we will create a root here, which is 8. We just created this, right? Now we will call this left function. Now the magic here is you need to remember one thing. What do you think is the maximum value that we can put in the left subtree of this root? Well, to hold a binary source tree's value, or hold it is a binary source tree, to hold that specific premise, we need to only send a value on its left subtree that is lesser than 8, right? So what I meant by upper bound is here the upper bound for the left subtree is going to be its roots value, or you can say 8 in this case. Again, think of it this way. If you are trying to build the left subtree, since you already built the root and then you are here, I equals 1, right? Then in order to build that, your value should be lesser, or your maximum value should not exceed your root. I mean, if you try to put 15 here, then that doesn't make sense, right? Because the binary source tree's left value should always be less than the root. So that's what I'm saying by the upper bound. So the upper bound here is 8, right? Now you will move your iterator from I equal to 1 to I equal to 2. Since you moved it there, you want to check your, and also you want to update your upper bound here. Your upper bound was 8. Now your upper bound has changed to roots value, which is 5, right? So your upper bound for creating a left subtree there is simply 5. Now you will check against 5. Since 1 is lesser in value than 5, so you can simply build the left subtree. I want you all to think about one thing. Why are we checking the we are updating the upper bound every time? Well, we need to update it every time because every time we create a left subtree, its parent is going to be changed, and then it should hold true for its parent, not only for the upper parent. So if we go down like this by changing every roots value for the upper bound, it's going to hold true for everything. Now we will update our I to be 3, right? Now the upper bound here was simply we can say integer maximum, or we can say infinity, and then for this root it is simply 8, and then for this it is 5, right? The upper bound. Now since we try to create again the left subtree for 1 7, but this doesn't hold true for this upper bound 5, or we can say 1 in this case, then we will backtrack here, and then we will try to create a right subtree from there. Again, it doesn't hold true, so we will go and backtrack to this section. Now we will call the right subtree, or we try to make the right subtree. Now the upper bound for right subtree is going to be the upper bound that we had here, which is 8, right? The maximum value that we can put on this specific section is going to be 8 itself, not 5. Because if we, this is the right subtree, right? And then it should be greater than 5. So the upper bound that we are trying to put in this section, or the that we are comparing, is the value that we got, or the upper bound of this section itself. So we're trying to put 7 here, and then we'll update our value to go to 4. And then since we can't put in either of these section, we will go backtrack and then go to the root itself and then try to put it on its right. Now what is the upper bound for the right section? Well, it is simply the infinity, right? We can put any values that are greater than 8. So the upper bound that we have given in the function, or we have so far, is going to be the upper bound for creating the right. Since this 10 value is lesser than infinity, then we can successfully create or construct the root there 10. Then we'll again move to 5, I equals 5, and then we'll try to put 12 on its left side. Now the upper bound for here is 8, right? Because for the binary source tree is conditioned to hold true, its left root or left subtree should not be greater than 8, or sorry, greater than 10. If it becomes greater than 10, then our binary source tree's condition doesn't hold true. So also our value is 12 here, and then it doesn't make sense because 12 is greater than 8. So we'll backtrack and then try to put 12 there, and we can successfully put 12 on that specific section. So that's the whole idea of creating a binary source tree using pre-order traversal. Well, let me write down the pseudocode of that specific thing here. Okay, so this is the function that we need to complete, that is given, which is given as pre-order as a vector. Now we need to construct another helper function to construct this binary source tree, because we are not only passing this vector, we are also passing the index value that we were using here, and then also passing the upper bound for every node that we're trying to build, right? So it's going to look like this. So we will simply say that is a helper function here. So we'll say that as a helper function, and then we'll pass this pre-order itself. So we will be passing that pre-order, and then we will pass the index value for every root. So it's going to be I, and then we will also pass the upper bound for every node, right? So it's going to be upper bound here. Sorry. Okay. That's the upper bound. Now as soon as we enter in the function, we want to create a root with this value, which is I, right? So we will create a new node or new root, which is going to be tree node star. Root is going to be new tree node, and then the value inside is going to be pre-order of I. So we're starting with I equals 0, so it's going to be pre-order of I, right? Now as soon as we create the root, we need to update our I value to make it I plus plus in order to go to the another index, right? And then we'll do that, and then we will try to build the left subtree, which is this simply. So roots left is going to be, in that case we'll simply call the helper function itself, because that's the recursive idea of creating the binary sort tree. And then in this particular scenario, we will pass the pre-order itself, and then we will pass I, and I has already been updated, so we don't need to update it again. Now since I said that we passed upper bound for it, that was, we will pass initially infinity here. What I'm trying to say is, we will create our I value to be 0 here, and then when we call that helper function, we will simply pass our pre-order and then I value, and then int max is the upper bound, because what is the upper bound for 8, right? The upper bound for 8 is infinity. What I'm trying to say is the maximum value that we can put in this root is, or the root's right section is basically infinity, greater than 8. So that's why we're passing int max there. All right, so we will pass int max here, and then in this case we'll simply say upper bound. Or no, for the root's left value, my bad, for the root's left value we had to pass the root's value itself. Why? Well, because if you see it here, 8 we just created, right? So what is the upper bound for 5 right here? Well, that is 8, right? Because we cannot exceed then 8, so we are simply passing the root's value itself that we just created, which was 8 here. All right, and then we'll also create a roots right, which is going to be also by calling the helper function, and then we will pass the pre-order again, and then our I again. Now in this case the upper bound is going to be upper bound itself. Why? Well, let's see here. From here, since our upper bound in this particular level is infinity, now we are trying to call it on the right side, right? The upper bound here should be greater than 8, and what is that? That is infinity, right? So we'll just passing the upper bound itself. Well, after we successfully calculate this, we will simply return the root, and that's it. So let's convert this pseudocode into the actual code and then try to submit that in LeetCode itself, right? So we have already initialized our index to be I equals 0, and then we also called our helper function. We'll return this helper function finally from that specific section. And then let's construct that helper function, which is going to be tree node star, and then helper, and then we got the vector of integer m percent pre-order, and then our integer value, and we'll pass it as reference integer I, and then we got the integer upper bound, right? As soon as we get the value I, we will construct a new node, which is going to be tree node, and then we'll call it root. It's going to be new tree node, because creating a tree is basically creating a node, right? And then we are passing pre-order of I. All right, and then as soon as we create that, we will increment our value by 1, and then again call the helper function for the left side. The value is going to be as it is for pre-order. I is going to be the same, and then for the upper bound it's going to be roots value. We'll again call same helper function for the right section by I, and then here the upper bound is going to be the upper bound itself that we got from our function call, which is this value, and then we will return the root here. Before returning root or doing something, we need to take care of base case too. So what are the base cases? Oh, well, if you see it here, your I value starts from this 8, right? As soon as your I value exceeds this 12 value, it goes out of bound. So you need to take care of that. If your I is equal to your pre-order dot size, and also you have another value, which is this upper bound. Well, at any section, if you were, let's say you are constructing for 5, right? Now, well, let's think about this. When you were trying to construct your binary search tree for the one's left side, the value was 7, right? Now, since 7 is greater than the upper bound, in that case, you will return null, or you will simply go out of bound, and then that's going to be your base case too. So we will simply say if your pre-order of I is greater than the upper bound given, in that case, we will simply return null. I hope you understood this. What I'm trying to say is here, if your given value is greater than upper bound, then we can't create a root in that section because it should lie less or lie behind the upper bound. Then only we can construct a tree, right? And I hope that makes sense. All right. So as soon as we do this, we can simply run the function, and let's see. All right, so we got an error here. It says, did you, oh yeah, we misspelled pre-order. I misspelled here too. Okay, it's gonna be pre-order. I hope everywhere I have spelled it correctly. Yeah, let's try to submit it again or run it again. I got an error again because I misspelled here too. Sorry about that. All right, let's try to run it again. Yep, so everything has been ran. Now let's submit it. Hopefully it has not been, hopefully it will submit. Yes, so it has been successfully submitted, and that's pretty good idea about solving the binary search tree or constructing binary search tree from pre-order traversal. Well, if you haven't understand this problem, or if you hadn't got any idea till now, I can suggest you all to watch the video again and then try to understand it, because it is pretty simple, and then the intuition will be achieved by solving this problem regularly 1 or 3 times. All right, I hope this makes sense. Thank you so much for watching the video. Stay tuned for another video.